Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to center our topics around the fundamental theorem of algebra. And what you need to know here is that this is a very detailed, very theoretical piece or section, I suppose, in pre-calculus. And as such, we're going to break it up into smaller chunks, a little bit easier to learn that way. So the way I have broken this apart is to really focus initially just on an introduction to the fundamental theorem of algebra, and then we'll break into other sections and other videos after that. So we'll start with something that doesn't seem like it's related to the fundamental theorem of algebra, but we're actually going to, this idea is going to really be key for us. So definition of a complex number. You should know this from your algebra course. However, it's nice to remind ourselves a complex number is a number that can be expressed in the form a plus bi, where a and b are real numbers and I is the imaginary number square root of -1. I is an interesting number, by the way, right? So I is the only number that when you square it, it becomes a -1. That's a reminder, but you probably know that. And because a and b are real numbers, so a and b are elements of the real number system, and because 0 is a real number, well, it turns out that either a or b or both could be 0. For example, 0 plus 0i, since those two numbers, 0 and 0, are both real numbers, 0 plus 0i is a complex number. So I'm going to write complex numbers above. And then let's look at some other complex numbers, like if a was 1 and b was 2, for example. So let me write that in here, plus 2i. Or if a was -3/4 and b was, oh, I don't know, let's do the square root of 2. And if you have it that way, often we write the I in front of the square root just because it looks weird if you write it this way. Here, I'll write it this way. It looks really odd if you do this for a couple reasons. One, because some people write square roots with a very long radical sign, and now you don't know, is that I underneath the radical or is it not? So just to be safe, it's better to write that I out front. Let's see, other combinations that are complex numbers. All these are complex numbers. By the way, I should also mention the obvious here. 0 plus 0i is 0, right? It's just nothing plus nothing. Another complex number, let's see, 0 plus 2i. That's a complex number. So in other words, 2i is a complex number. Another complex number, 3 plus 0i, or in other words, 3. And this brings up a very important point about the complex number system. If you've ever seen any of my videos on number systems, you know that the smallest number system that we have is a set of natural numbers. The set of natural numbers are the numbers like 1, 2, 3, and so on and so forth. And then that set is contained within a slightly larger suitcase of numbers called the whole numbers. By the way, I'll label these. That's natural numbers. This will be the whole numbers. Okay. And the whole numbers contain 0 and then 1 and 2 and 3 and so on and so forth. That is contained within a big suitcase called the integers. And the suitcase called the integers contains all of those numbers, those whole numbers, those natural numbers, along with -3, -2, and -1. Right? So the negative versions of the whole and the natural numbers. And then that suitcase is contained within an even larger suitcase, which are called the rational numbers. And the rational numbers we use the letter Q for, because they're like quotients of things. And these are numbers like 3/7 or a -1/3. but it also includes numbers like 3 over 1 or negative 6 over 3, which would be negative 2. So all of those previous numbers we've mentioned, those are also rational numbers. So every time you talk about a natural number, you're really talking about a whole number as well, but you're also talking about an integer, but you're also talking about a rational number. And then we have this weird suitcase of numbers that is off to the side, and it's actually, the way I'm drawing it is slightly incorrect. I should draw it this way because it's actually much bigger than the suitcase of rational numbers. It's a suitcase of irrational numbers. Now, I'm sure there's a notation for the irrational numbers, but I don't recall ever seeing one. Or if I have, I think it's an I with a double bar, which looks like the Roman numeral 2 to me, so I'm not going to use it. However, the set of irrational numbers does not contain any of the rational numbers. These are disjoint sets, but the set of irrational numbers contain numbers like the famous number pi, the famous number e, the not so famous number square root of 2, square root of 3, and so on and so forth. These are numbers that don't have terminating or repeating decimal expansions. They just go on forever. There's no pattern to their decimal expansions. So that's what irrational numbers are. And it's a larger suitcase because actually there's more irrational numbers than there are rational numbers. And you might say, wait a second, aren't there an infinite number of rational numbers? The answer is yes. And aren't there an infinite number of irrational numbers? The answer is yes. But they're different orders of infinity. This is also known as the cardinality of the set, but you don't need to know that. That's not that big of a deal for us. So anyhow, those are the briefcases or the suitcases that showcase kind of the numbers that we've dealt with. And you should know that that group of numbers, you can glue those two suitcases together, and that would be, I'm using red on purpose, the real number system, when you glue those two suitcases together. Now notice, we have a new number system called the complex number system, and it contains numbers like 0 and numbers like 3. It will also contain numbers like pi, because pi is a real number, so another complex number would be pi plus 0i. So therefore, pi is also considered a complex number. In fact, all this big old suitcase of real numbers, they're also considered complex numbers. However, there's yet a larger group of them, and that is all the complex numbers with non-zero imaginary parts. So there is a huge suitcase, and let me see if I can zoom out far enough here. And this huge suitcase, which I'll try not to overlap too much. There we go. Boom. Now it starts to look like a car, I guess. Anyway, or a dog, right? Here's his ear. Anyway, all right. So this huge suitcase here is the complex number system. I'll use a C for that. And outside of the real number part of it is going to be complex numbers with non-zero imaginary parts. So for example, 3i is in there, and 1 minus root 2 times I, and I don't know, it doesn't really matter, 2 minus I, that type of thing. So all of those non-real numbers are still called complex numbers, but then real numbers are also complex numbers because they are of the form a plus bi, but the b part is 0. So this has grown our number system quite significantly to be very massive. And by the way, I mentioned at the top, real numbers are also complex numbers. Not the other way around though. And there you go. But not all complex numbers are real numbers. There you go. By the way, the word real versus non-real, or real versus imaginary, that is a misnomer. The imaginary numbers like I and 2i and stuff like that, those are incredibly important for real things to happen. So when somebody calls it imaginary, it's because when they were first discovered or first kind of run into as part of solutions to equations, nobody knew what to do with them. And they figured they're probably fairly useless. And so they were called imaginary. But in reality, they are very useful for electronics. That's why your phone, your TV, all that stuff works, is because of the imaginary numbers. So not so imaginary now, are they? Now I want to draw your attention to a really good visualization of what a complex number system does for us. So right now what you're staring at is the x-axis versus the y-axis. Ignore this key here because the person who coded this improperly labeled this key. It's actually, the red axis definitely is the x-axis. The green axis, the blue axis is the y-axis. Oh, I'm sorry, that is true. So he did actually label that fine. But his still, the way he has labeled, he says the z-axis is the blue axis, which is the y-axis, yet he calls the y-axis something. Just ignore the key. All right, just look at this graph right here. This is the horizontal axis, or the x-axis, and the blue axis right there is the y-axis. That makes sense. And we're looking at ax squared plus bx plus c, or I should say y equals ax squared plus bx plus c. Specifically where a is equal to 1, so it's 1x squared. B right now I'm just letting to be 0, so plus 0x plus 1. So it's basically 1x squared plus 1. I could adjust that to be 3.2, or I could go down, right? So it doesn't really matter. I mean, all this is the vertical shifts that we've experienced so far in this course. You could change B. This is what happens when you move B around. Nothing big, right? But I'm going to keep it on the axis for right now. Now, what you should note about y equals x squared plus 1 is that it doesn't have a 0 that you can see. The 0 for this function is non-visual because, or non-visible, or invisible, I guess is the proper word, because the zeros for this are actually in the complex plane, not on the real axis. So we don't have any spot where this function would ever become 0, because x squared plus 1, if you were to want that to become 0, you'd find out that that becomes 0 when x squared is a negative 1, or in other words, when x is equal to plus or minus the square root of a negative 1, which we know is I. So this, you cannot plot that on the x-axis because the x-axis and the y-axis, those axes only represent real numbers. If somebody's never told you that before, shame on them. You are only graphing, when you graph in algebra, on the real number coordinate system, so the real Cartesian coordinate system. As you move forward and progress in mathematics, you might, it's not always necessary, but you might need to graph in the complex number system, and there's some beautiful theory behind that. However, I want to draw your attention to visualizing the complex plane. So there's actually a hidden magical world that sits here. And if you're like me, I played D&D my entire life. And so I'm used to the concept of seeing our visual world, or the world that we live in, the prime materials, what most D&D players would call it. And knowing that there's a hidden plane behind the scenes that you don't know, that there are a lot of little worlds attached to our world that are linked to it in little weak spots. And in those weak spots where those links are made, there is, we can hop over to that other world, whether it may be the ethereal realm, or it might be some celestial realm, whatever it is. Okay, so let's go ahead and get a look into that other realm right now. So here's that function. It's still 1x squared plus 0x plus 1. But now I'm going to grab this and turn the world slightly. Now I'm looking at this from a different perspective. Again, the red axis is actually the x-axis. The blue axis is still the y-axis. But now we have a third axis in there. And that third axis is called the complex axis, or the imaginary axis. And if you look, there's a reflection of our picture. And not only is it rotated what looks to be 90 degrees, but it also gets reflected about its, I guess this, you would call it its vertex. So if you can imagine reflecting this red curve about its vertex, so it flips upside down. I don't know if I can do that, but I can't. So, well, okay. Imagine it gets reflected, and it gets reflected upside down, just like that. And then it gets turned into the wall 90 degrees. That's exactly what it happens. So again, it gets reflected to be upside down and turned 90 degrees, and there is the complex plane solution. You are looking at a different world right now. And if you look at the solutions there, it's kind of hard to see. I wish I could zoom in. Maybe I can. Well, how do you do? There you go. So you could see that those solutions are -1 and 1, but they're not -1 and 1. They're -1 and 1 on the imaginary number line. So it's -1i and 1i. And remember, that was the actual solution to that equation. That was the actual 0, is x equals plus or minus 1i. Now the visualization here is so awesome that I'm going to go ahead and I'm just going to play with this for a moment here. So we're back to looking at the x-axis versus the y-axis. And let's go ahead and I'm going to adjust b. Maybe I'll adjust it this way. Maybe I'll add to the c value slightly to lift it up. Now remember what I said. The complex solution. So right now, there's no 0. There's no real 0 because it doesn't hit the x-axis. Okay? It doesn't hit this x-axis. You only get a 0 when your curve hits the x-axis. That's when you get zeros. So if I were to lower this down right there to where it lands on the x-axis, I have a 0 of multiplicity 2 actually, because it bounces right off. If I lower it even further, I get 2 zeros for this curve. So this should not be new to you because we've been going through this. However, what happens if I raise it above the x-axis and you think there's no more zeros? And I tell you, yes, there are actually zeros. You're just not looking in the right world. If you would just flip that upside down and rotate it 90 degrees, you can see your zeros right there. They are at -1i and 1i plus something. And in fact, the plus something, you could say, I'm just going to ballpark this, okay? But it looks as though, what is that, about a half along the red axis? Ooh, that just started spinning by itself. So if you think about along the red axis, those green dots are about a halfway through the red axis. So I'll just say the x values are 0.5. And in the imaginary direction, they're at plus or minus 1. So the actual zeros for this function that doesn't look like it has zeros are going to be roughly 1/2 minus I and 1/2 plus I. That is the complex system. So beautiful. Such a gorgeous system. By the way, I was just about to jump away from this and then I thought, you know what? I should kind of showcase what happens when you drag that down. So again, the red axis is the x-axis, the blue axis is the y-axis. If I bring that down to where the function dips below, right, just for a brief moment, then notice I have 2 zeros for my red function there. But if I rotate, if you imagine that flipping upside down and rotating 90 degrees, that resulting parabola on the complex plane will not hit any axis at all. And so there's no such root from the complex plane. Only the 2 roots for this second degree polynomial that exist on the x-axis. And even if I dip this down further, I'll still only have 2 roots because remember, to see the complex solution, you would flip this upside down and rotate 90 degrees into the complex plane. But once you rise above, there's no real roots or no real zeros, but when you flip this red curve and rotate it 90 degrees, you have 2 complex zeros where it hits the complex axis or the complex plane. Very, very, very beautiful theory here. And I should give credit where credit is due. That's a GeoGebra applet. So it's at geogebra.org/m/ all that stuff there. U2HRUFDR with some capitals and lower cases in there. And it was written by Aaron Glancy. Very beautiful visualization of that. Let's go ahead and use that to talk about something supremely important in algebra. Are you ready for it? The most important theorem in algebra? It is really short. Every polynomial with complex coefficients has at least one complex zero. By itself, honestly, the fundamental theorem of algebra is not like impressively awesome by itself, but their corollaries get attached to this that make this very, very powerful. I want to say before we go any further that the proof of this theorem is beyond the scope of a pre-calculus course or any other lower division course. You usually would do a proof of this in upper division mathematics. So let's catch a visual of this just to convince you, maybe not to prove it to you obviously, but to justify the logic. We'll start simple. Here's a polynomial, the graph of a polynomial. You know it's the graph of a polynomial because one, it's smooth and it has end behavior that mimics either x cubed or x squared. That is pretty much why I know this is the graph of a polynomial. Now, I can't guarantee it, but it is. All right, so look at this guy, and remember the theorem says every polynomial with complex coefficients, remember complex numbers are all real numbers, and those with imaginary parts as well. So any polynomial that has coefficients of the form a plus bi. It could totally have weird coefficients, totally fine. Anyway, any polynomial with complex coefficients has at least one complex zero. Again, remember, to have a complex zero means you have a zero that's either a real number or a complex number with an imaginary part. Well, if you just look at this, there's a real number zero right there. I don't know what it is, but wherever it hits the x-axis, we know we have a real numbered zero. So yeah, I guess this theorem looks to be kind of true so far, but we could always create examples of polynomials that don't strike the x-axis. Those are the ones we're really curious about. So let's take a look at some of those. Here we go. Here's an upside down parabolic shaped polynomial, and it doesn't look like it has any zeros at all. However, it does according to the fundamental theorem of algebra. It doesn't have any real numbered zeros. However, there is a hidden axis out in space here that goes back into the board and out into the world. And this hidden axis, we will go ahead and call, let's just call it the z-axis for now. And we know that if we rotate this, maybe I should say, if we flip this graph, and I'll sort of draw that right here. If we flip this graph upward, I'll just do it like this so that I can erase it. So we flip this graph upwards and then rotate it 90 degrees. So that's going to be tough for me to show you because I'm not an artist. But if we flip the graph and rotate it 90 degrees, it will be an upward facing parabola crossing the complex plane. And let me just see if I can do this. Now, I don't know if visually your brain can see that, but that is flipped upwards and then rotated 90 degrees to be intersect this z-axis, which is the complex axis. Again, not necessary for this course or for any pre-calculus course, but I still think it's really, really cool. So those two green dots would be the complex zeros of this equation or of this function. Now, what I don't want to do is get into higher degree polynomials because those get a little messy. And so it's not, drawing that is not going to be fun. So instead, I will just say that this carries forward as we move forward, that these curves, all polynomials, can either strike the real x-axis or not. But if they don't strike the real x-axis, they are going to strike the complex plane. They might even strike that blue complex axis or imaginary axis, but they'll definitely strike the plane that's complex. And just to show you how complex that could be, here's a crazy example of it. I don't think that it's worthwhile to even bother staring at this, other than to note that they have, looks to be some sort of cubic here. And then this is the complex intersections. You do not need to know any of that, but kind of cool, I guess. But I'm not willing to fiddle with it other than to play with it like this just to see what happens. But other than that, this is well beyond the scope of the course that you're in. But the cool part is the one that I already showed you, which was this guy right here. So just to remind you, such a beautiful picture. And if you have a curve, you should know from this point forward that if you have a polynomial that never touches the x-axis, by the fundamental theorem of algebra, there's a little hidden plane. A different world where your function actually does strike a hidden plane. All right, we're done with this video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.